Welcome to a long version of my presentation for the paper Reasoning Shortcuts in Infinite Domain Constraint Satisfaction, Algorithms and Lower Bounds for Backdoors. So I'm Victor, and this paper is joint work together with Peter Jonsson and Sebastian Ordyniak. The short selling point and main motivation behind our paper is that we have these so-called constraint satisfaction problems. And it is possible to solve them by using various types of techniques from constraint programming, for example, local consistency and propagation. And for finite domains, so the case where the domain of the variables in question is finite, everything is known about the classical complexity. So we know precisely which types of problems are tractable in P or NP-hard. So everything is known. And quite a lot is also known about the NP-hard cases of these problems with respect to, for example, parameterized complexity, which offers a more nuanced view of the complexity. On the other hand, if we consider infinite domain CSPs, this expressive power makes it possible to model different types of problems. Some problems that cannot really easily be formulated as finite domain CSPs. And quite a lot is still known about the classical complexity for these problems. But much less is known about, for example, parameterized complexity. So we don't really know that much about the complexity of NP-hard cases of infinite domain CSPs compared to the finite domain case. And in our paper, we consider a particular topic within parameterized complexity, so-called backdoors, which have been successfully used and defined in the finite domain world, where they make a lot of sense, we have nice algorithmic properties, but they have barely at all been considered for infinite domain CSPs, which is what we do in our paper, and we obtain a general definition and general algorithms. So as a simplification, finite domain constraints, for example, makes it possible to formulate satisfiability problems, scheduling problems, and various types of coloring problems. And it is possible, I would argue, to solve all of these different types of finite domain constraints using quite uniform algorithms. So we know essentially how to solve even hard instances of these problems, in a lot of cases at least. But of course, this is a simplification, so don't take everything word by word. This is a simplification. And if we turn to infinite domain CSPs, then we can, for example, formulate many interesting types of problems from artificial intelligence. For example, Allen's integral algebra and the so-called region connection calculus. And these problems cannot easily be formulated as finite domain CSPs. But it is also possible to have problems with a slightly more logical flair, where we consider relations defined with respect to some underlying relational structure. For example, maybe as equality or maybe the rational numbers with the natural ordering. And I'm going to return to this later and give you some additional details about these problems. So this is just an overview. And for these problems, so they are well studied, and especially for these reasoning problems, it is desirable to be able to solve them as fast as possible. But there are a few general techniques that works for all of these problems. So essentially what you need to do in the infinite domain world is to take it problem by problem. So it's harder to find uniform methods applicable to all different types of problems. But of course, this is a simplification. Don't take this word by word, but at least there's some truth to this, that it's harder to have these uniform arguments for infinite domain CSPs compared to finite domain CSPs. So how is it then possible to solve finite domain CSPs so efficiently? And especially, how is it possible to solve SAT problems so efficiently? Because modern SAT solvers can solve instances containing possibly millions of variables and quite fast. And a partial explanation is based on backdoors. What this means is that one tries to find a small fragment of a problem, such that once we fixate every variable in that small fragment of a problem, the rest of a problem becomes tractable. So essentially, the actual complexity for solving this problem could be dominated by this small hard fragment, this so-called backdoor. So roughly meaning that the hard, large instances of SAT can still have islands of tractability. And our question is whether it's possible to use backdoors also in the context of infinite domain CSPs, and in particular, whether it's possible to have a nice general definition applicable to all of these different types of problems which I've mentioned. Here's a short line for the rest of the presentation. So we are first going to properly define constraint satisfaction problems, then looking at backdoors both in the finite and infinite domain setting, followed by a summary of our results and some open questions. But let's begin by properly defining constraint satisfaction problems. So really the only complicating factor of this definition is that I'm considering a so-called constraint language, and I use this as a parameter to the problem. So this constraint language, well, it's just a set of relations over some underlying domain, typically called D. And the constraint language then determines the types of constraints that are allowed to appear within an instance of the CSP problem. So every constraint is formed by taking some variables, combining it with some relation from this constraint language. And the question is just whether it's possible to find a satisfying assignment. So an assignment from the variables to the domain consistent with every constraint. Simple example in the finite domain world would be Boolean constraints. So assume that we have a Boolean domain and consider this ternary relation. Then the CSP over this relation would be an alternative formulation of 1 in 3 set without negation. So each tuple here specifies which of the 3 variables should be 1 and the other ones have to be 0. In the infinite domain world, this is a quite nice example, integer programming, or a kind of feasibility variant here. Where the domain, well, that's just the set of all numbers. And we then consider constraints where every relation is the set of models of a constraint according to the following formula, where a1 to ak are some coefficients and x1 to xk are the variables in question. So this problem can't really easily be formulated as a finite domain CSP. Another example is Allen's integral algebra, where the domain consists of pairs of real numbers, describing start and endpoints of integrals. And we then have some basic binary relations, which we can, for example, use to say whether one integral directly precedes another integral. And normally, to obtain a slightly more interesting problem, one also allows a union of these basic relations too, which makes it possible to express compound statements with respect to these basic relations. And slightly more generally, it's quite common to first fix some relational structure. So we have some universe, we have some relations of that universe, and then consider a CSP problem where every relation is first order definable over this fixed relational structure. And during this presentation, so I'm not going to use any fancy relational structures. I'm just going to assume the simplest possible case where actually we don't have any additional relations at all. So the only type of constraint that we allow, the only type of atomic constraint is just the equality, or of course the negation of equality, so inequality. And an equality language can then just be defined as a set of first-order definable relations over the empty relational structure, or equivalently, just as over an relational structure containing equality and inequality. And an equality CSP, well, that's just a CSP over an equality language. Simple example is this ternary relation, call it S, defined in this way. So it's true for two distinct cases, either x is equal to y, or, x is equal to y and x is not equal to z, or x is not equal to y and y is equal to z. We have these two distinct cases. And then this CSP is known to be NP-complete. And even better, with regards to classical complexity, everything is actually known for equality CSPs. So we know exactly when they are polynomial unsolvable or NP-complete. Let's now continue by properly defining finite domain backdoors. So the idea is that we want to simplify some given CSP with respect to a partial assignments of the variables. So assume that we have a partial assignments of the variables and think about how we can use that partial assignment to simplify a constraint. So what we do is essentially to remove every tuple from this relation, which is not consistent with the partial assignment. So for example, if I have a partial assignment where x1 should be, say, 0, and I have some other tuple, some other assignment to this relation where x1 should be, say, 2, then I'm just going to remove that entire assignment because it's not consistent according to this partial assignment. And if I have some variable that has been determined by this partial assignment, I just try to break it away. And I use this notation to denote this simplified constraint. Then in the best case, what I could hope for at least is that I'm able to simplify all my constraints in a suitable way and maybe even obtain an instance of a tractable CSP, even though the original instance might have contained some harder constraints. And this leads to the following general backdoor definition. So we assume some underlying set H of CSP instances. So probably this is going to be some nice tractable set of CSP instances. And then we define a backdoor with respect to this underlying set H as a subset of variables where every simplification corresponding to some partial assignment results in an instance belonging to this class. And the nice thing about backdoors is that it can be found efficiently and it can also be used to efficiently solve hard CSPs. And these are two fixed parameter tractability results. So they hold if the size of a backdoor is not too big. In practice, this is still very good because we do expect even hard instances to contain reasonably small backdoors, at least for lots of real world instances with a lot of hidden structure. And then, so if backdoors are so great, then of course we want to be able to use them in the infinite domain CSP setting as well. But there are several problems with this. So it's not a straightforward generalization. So the first obstacle is that we can't even enumerate functions of this form. So we have an infinite number of partial assignments, even if this set is B is small. And this can, in practice, be circumvented for lots of infinite domain CSPs because we can kind of group these partial assignments together according to automorphisms. But this second problem is not so easy to overcome in comparison, because it's not clear at all how we can actually use these partial assignments to simplify constraints in a nice way in the infinite setting. So in principle, we could take the finite domain definition and try to use it, but it's hard to find actual applications of that definition. So here's an example showing why we have a problem. So recall the definition of this equality relation. And if we have some partial assignment where Z is equal to 1, then of course, we'd hope to be able to simplify this into something, maybe a binary constraint, but we can't really do that in a nice way, because in an equality CSP, we don't allow these constants. So this would not correspond to some tractable equality CSP. And this problem is not isolated to this single relation or to equality CSPs, but it's a more general problem for the infinite domain CSPs that are studied in practice. So it seems to be the wrong objects to enumerate these partial assignments, because we can't actually do that much with these concrete assignments. And we do manage to overcome this in our paper, and I'm presenting you these definitions, not that I'm hoping to be able to explain them during this presentation, but just to show you that it is non-trivial to even define all of this in the infinite setting. So a warning, this is not a simplification. So these are the actual definitions that we have in our paper. Some of the main ideas are that we consider a language triple, consisting of a base language, a target language, and a source language. And crucially, so the important idea is that we don't enumerate simply partial assignments, but we enumerate subsets of pairs of variables. And then we enumerate functions from these pairs of variables to relations from a base structure. So we concentrate on enumerating various types of relationships between the variables. So in the equality CSP setting, we really only care about whether two variables are equal or not equal. So this would be a concrete example of this, which is particularly simple. So here the base and target language would just be the same. We have equality and inequality, and we attempt to simplify everything to binary equality constraints, which we could do in this example if we have a set B containing x and y, and if we know that x and y should be distinct. Then according to the definition of this relation, if they are distinct, then y has to be equal to z. So we can really simplify it. And one of the hardest part of the paper was to come up with this general definition, and to make it general enough to capture a sufficiently broad class of infinite domain CSP languages. But we do also obtain actual algorithmic results. So we do prove that backdoors, according to our more general definition, can be found efficiently, and they can be used to efficiently solve CSPs, provided that the languages in questions are finite. And don't confuse this finite here, so finite amount of relations, with the finite domain CSP. Don't confuse these two concepts. And it turns out that this assumption that languages are finite, it is actually crucial, because we do manage to construct some infinite languages where the backdoor detection problem is probably not in FPT. So to summarize, we studied backdoors in the context of infinite domain CSPs and obtained a general definition applicable to lots of problems, and we also obtained algorithmic results. So this sets our work apart from existing results. And of course, it might still be possible to obtain some better results for concrete classes of infinite domain CSPs. So if we concentrate on, for example, Allen's interval algebra, could it be possible to find a better notion than a backdoor? And it would also be interesting to say something about the backdoor detection problem for infinite constraint languages. Maybe it's still possible to find some examples of non-trivial infinite constraint languages where the backdoor detection problem is interesting.